This is the project we have made
Recording in progress.
for our class 573. Our project name is RoboNurses, and this is the logo. And I, Trina, and Larry, both of us contributed in equal amount work for making this project work.
Okay, so the overview of the project at a high level, what we're trying to do is we want a system that will automatically deliver medications to patients because in like hospitals and whatnot, there may be many patients to manage, and we want to reduce the nurses' workload, and so by maintaining a database of medications and patients with the room numbers and the expected delivery times, we can send out a robot to the expected room for the patient to drop off specific medications at regular time intervals. And the robot can identify that it's delivering medication to the correct patient. And so main features of our project include an IoT hub for maintaining or for monitoring the robot's position, statuses of deliveries, and that is the main premise of our project. So let's go to the next slide. So at a high level, on the left image there, we have our robot in the bottom left, and then we use an MQTT protocol to message between the robot and the central processing node. All decision making is done by the central processing node. The central processing node also manages the dashboard, and it will store the responses from the robot, the delivery statuses of each medication inside of a database, which can be viewed. And then on that far right, we can see it's just broken down a little bit more. The MQTT, go back up, Trina. Yeah, on that far right, we can see the MQTT protocol is broken down a little bit more by topic. So it shows which ones the robot is publishing to and which ones it's subscribing to, and also the same is said for the central processing node. So go to the next slide. Okay, and then here's the actual workflow of our application. So we didn't implement as much as we wanted to, but we begin with the central processing node sending the medication delivery request to the robot in that top left. And then if the robot is available to deliver medication, it's going to move forward until it gets to a box. It moves in 90-degree. Our environment's kind of fixed to support the robot, but okay, so bear with me. It moves forward until it gets to a box. Once it gets to a box, it's either going to turn left or turn right. It will take a picture attempting to identify a room. It sends that picture to the central processing node. The central processing node will send that to the cloud to identify the room number, and it will extract the results and send it back to the robot. The robot's then going to move forward up until that room. If it's the target room, then if it's not the target room, then it's going to turn again, and it's going to repeat that same process over again. It's going to try to identify a room and same thing. But if it is the target room, then the robot's going to attempt, or it will take a picture of the patient. It will send that to the cloud for patient recognition. Or it sends it to the central processing node, which sends it to the cloud for patient recognition. And the results are sent back. If patient's identified correctly, medication's delivered. If not, no medication's delivered. Okay, next slide, Trina, and all you.
Yes, thank you. So for central IoT have we have implemented SQLite DB for leveraging all the DDL and DML operations of a database. So here we have used three tables, robot details to capture all the robot movement, and the table gets updated very frequently. So we have restricted the data for displaying. So in the central IoT hub we are only displaying the latest 10 data for robot movement. And then we have patient details where we'll store all the patient related data. And there is another table which is delivery status. Here we are retrieving all the delivery status from the robot and updating the table, and it will show either success or failed. So now here we have we have used couple of services. So the edge based services has been used for automated medication delivery, and for the cloud based services we have used Azure portal for and for in the Azure portal we have leveraged the custom vision properties to make our model trained for patient image as well as for room image. And the robot movement tracking is also a cloud based services. So now we can show the demo. So here we can see like there are two custom vision API we have used. One is for room recognition and another is for patient recognition. And this is the demo for use case 1 for central IoT hub, where we are assuming that where we are testing that the robot will identify the room as well as the patient, and the robot will deliver the medicine to the patient and update the delivery status. This is the second part of the demo of RoboNurse project. So here our objective is to identify the room and identify a patient and then deliver the medicine to the patient. And if the robot is not able to identify a person or an image as patient, then it will send back the delivery status and as failed, and the delivery status and the success rate will be displayed in the dashboard which we have built using Node-RED. And we'll keep track of the robot movement and it will be displayed in the dashboard. So the flow starts when we are sending the medication request from Node-RED to the robot. Here once I am sending the request, so the robot is starting to move. So now we are seeing that it is actually finding the room R0. So after that the robot will stop and it will take the picture, and you will see like and now in the Node-RED we need to subscribe the picture, and we have some Azure model where we'll see like if where we have trained the model for recognizing the room as well as the patient. So here from the console we can see that the robot has identified the image as patient, and it has delivered the medicine to the patient. So it sends back the response as success, otherwise it will be failed. And from here we can see the accuracy rate is 50% because the success is 5 and failure is 5, because earlier we can it might happen that it failed for 5 times, so it's now 50%. Now if we just take a look at the dashboard, we'll see this is the robot activity details. So this is the robot's x coordinate, this is the coordinate, this is the forward velocity, and this is the angular velocity, and this is the head angle, and this keeps changing. So once we will get all this, once the robot starts moving, so it keeps changing very frequently. Now this is the demo for use case 2, where the robot will be able to identify the room, but it will not be able to identify the patient. Demonstration of use case 2 for the central IoT hub, where we are sending the request to the robot, but it will be able to find the room, but it will not be able to find the patient. So the model, the custom vision model, will recognize it as non-patient, and then it will send the response, and in that case the robot will not deliver the medicine. So now we can see that the robot is able to identify the room as R1. Then the next thing is it will capture the data, capture the image of a patient, and then it will send it back to the central IoT hub for validation. And then central IoT hub will leverage the custom vision API for recognizing the patient face, and it will validate the image and send it back to the robot. And if it's not a patient, in that case the robot will not deliver the medicine and update the delivery status as failed. So here we can see that the image the robot has sent is a not patient. So in that case the robot will not deliver the medicine, and it will update the delivery status as failed. So here we need to check the first delivery status, it is failed, because we are getting all the data in a reverse manner. So that we'll get the updated one. And here we can see all the information about robot movement, and will display all these things in the Node-RED dashboard. So if we go to the RoboNurse, so here we can see this is the robot activity details. It keeps changing once the robot keeps moving, and this is the last 10 movement details of the robot, and this is the accuracy rate of a robot delivery status. So here it is almost 50%, because the success is also 13 and the failure rate is 13. So we can say like there needs some improvement of that robot mod.
So a robot's going to attempt to find room 0. First moves forward before taking a left. After taking a left, takes a picture, sends that to the cloud for identification. It then takes another left, takes a picture. If it identifies it correctly, it will stop, and it just stopped, indicating that it has found the correct room. Otherwise, it would have turned towards room number 2. That means it delivered medication. Okay, so challenges with our project. There were a lot. Let's start out with the robot. First off, it doesn't move very predictably. So the videos you just saw took many runs to successfully get our use case working. It doesn't always move straight. Also, as the battery starts to die, that it loses charge. It doesn't turn as much as it used to. So our implementation highly depends upon calculated angular rotational velocity and forward velocities. So as it dies, it starts to like do half turns, and then it doesn't do what we want it to do. So that was hard. And even when it goes straight, it doesn't always go straight. It hits bumps, or the wheels don't get the same amount of power, so it starts to turn, and it goes all over the place sometimes. There was difficulty implementing the extended Kalman filter using the available sensors. I couldn't come up with a good way to update or to perform filtering using the images that we captured using the Raspberry Pi camera and the infrared sensors in the front. Additionally, we had issues with our machine learning models, identifying the rooms correctly and identifying the patients. Okay, next slide. So for future works, we'd like to spend more time on the extended Kalman filter, getting that updated using the images and the infrared sensors only. And this would definitely help the robot's belief state. Additionally, it would be good to send the believed landmark positions up to the cloud and display that in a map that we kind of build dynamically with time. Right now, we just store the believed landmark positions on the robot. We don't do anything with them. And then we would like the robot to return back to the medication room after a delivery instead of just stopping there and having to be picked up. And a better search algorithm would be better. Right now, it's hard coded to turn left 3 times, I believe, and then it turns right once for the last room. And then we also need to improve our machine learning models to correctly identify the patients. We would set a phone in front of the Raspberry Pi camera with the correct patients, and it would work most of the time, but sometimes it didn't. And then in identifying the rooms, it didn't always identify them correctly, so we'd like to improve upon that. And that is our project, so thank you very much.
Yeah, thank you.